अच्छा जी, आपको मेरी स्क्रीन नजर आ रही है?
आओ सर, राजी पर नजर की सर।
और चलो जी, बिस्मिल्लाहिर्रहमानिर्रहीम शुरू करते हैं। पहले हम जो है वो ये क्लास तकरीबन 10:15 या इस वक्त तक जो है वो विल ट्राई कि एक ही स्ट्रेच में जो है वो 2 घंटे में इसको ख़त्म कर लें। 10 और 10:15 के बीच में इसको ख़त्म करेंगे, फिर छोटी सी ब्रेक होगी और इसके बाद जो है वो क्विज होगा। क्विज तकरीबन जो है वो 10:25 पे जो है वो शुरू होगा। ठीक है। और मतलब 35 मिनट का जो है वो क्विज है। वो आपने जो है वो सबमिट करना होगा। ठीक है ना। और गूगल क्लासरूम पे ही जो है वो सबमिट करना है। लेट सबमिशन और इस किस्म की उसकी कोई गुंजाइश जो है वो नहीं है। ठीक है। अच्छा जी, हमारी डिस्कशन जो है वो जो मैकेनिक्स ऑफ सॉलिड 2 में हमने पहले जो है वो जो कंबाइंड स्ट्रेसेस है यानी स्ट्रेस एट ए पॉइंट, कंबाइंड स्ट्रेसेस की बात की, फिर स्ट्रेस ट्रांसफॉर्मेशन की बात की, स्ट्रेन ट्रांसफॉर्मेशन की बात की। ठीक है ना, जिसमें हमने मुख्तलिफ जो है वो टॉपिक्स जो है वो डिस्कस किए। ठीक है। आज की क्लास जो है वो हमारी जो होगी वो इलास्टिक कांस्टेंट से रिलेटेड होगी। ठीक है ना। आज की क्लास हमारी जो है वो इलास्टिक कांस्टेंट से रिलेटेड जो है वो होगी। ठीक है। इलास्टिक कांस्टेंट जो है वो उसमें क्या रिलेशन है, कितनी इलास्टिक कांस्टेंट्स होती हैं, और आखिर में इस क्लास के आखिर में जो है वो हमारा जो बड़ा टॉपिक है, मेन जो टॉपिक है वो थ्योरीज ऑफ फेलियर है, उसको हम डिस्कस करेंगे। ठीक है ना। सो शुरू करते हैं आज के उसको जो है वो इलास्टिक कांस्टेंट जो है वो उसको शुरू करते हैं कि इलास्टिक कांस्टेंट जो है वो क्या चीज़ है। इससे पहले जो है वो यहाँ पर मैं चलो एक स्लाइड जो है वो इंसर्ट कर देता हूँ, जिसमें जो है वो मैं कुछ जो है वो क्वेश्चन एडिटर से जो है वो
अस्सलाम वालेकुम सर।
जी जी।
सर्दी की गफ़ार नर दे सर, इंग्लिश की वो है सर।
ओके ओके ओके। Dear foreigner, what is your name? You'll have to remind me. Okay, if I'm speaking in Pashto and Urdu, then you will have to remind me. Okay, let me, I'll have to take some time. So let's, X, Y. Y, Z. Uh, Z. ये कैसे ज्यादा होंगे, आई डोंट नो। ज़्यादा 6/6 संग कन्वर्ट कीजिए।
सर्दी کې دغه نشته دا دغه شان دي کې انټر باندې کېږي سر.
نو دا نمبر اف دغه به څنګه زیاته ہے؟ دا خو به زیات شي خو عجیبه خو نشته د جوړ شو. دا خو وشي خو دا نمبر اف دغه چې کوم دی نو नंबर ऑफ कॉलम्स कैसे इंक्रीज होंगे? Number of columns. पता नहीं कैसे इसमें there is no option in this case. तो इसी से काम चला लेते हैं फिलहाल। Six. Six, one. Six. Okay, so this is relation. इस पे जो है this is a generalized form of stress strain relation. ठीक है ना? Let me just copy this. As a reference मैं इसको यहाँ पर जो है वो रख देता हूँ. So let's put it as a reference here. So stresses are related to strains. Okay, and the relation between the stress and strain is made by elastic constants. Okay, elastic constants. Now there are, you know that in a three-dimensional state of stress, a maximum of 6 independent stress component exists. Yeah, 6 independent component of stresses, and corresponding to these 6 components, these are the 6 components. Corresponding to these 6 components, there are strain components, 6 strain components. Where is the subscript of this? So there are 6 strain components. These 6 strain components are related to these six stress components through elastic constants. This is a 6 by 6 matrix, meaning that sigma x is the normal stress is equal to E11 into x1, E12 into epsilon y, E12 into epsilon z, and some of the components are 0. Okay, 0 are also the next, because the normal stress is not related to the shear stresses. So there are first 3 components and then 3 zeros. Okay, similarly for this 3 component and 3 zeros, for this 3 components and then 0. Okay, so and then you have tau xy is related to only gamma xy, so the rest of them are 0. Tau yz is related to tau yz, and this is the case only for isotropic material. So if you just count these elastic constants, so this is a symmetric matrix. So the number of elements in this matrix are 6 by 6, mean 36 components. Okay, but since this is a symmetric matrix, so this right diagonal is having 6 components, and there are 15 on this side and 15 on this side. So these 15 are similar to these 15. Yani E16 is similar to E61. Okay, E16 is similar to E61. Okay, and similarly the other components. So if you just count them, these 15 are similar to this one, to this 15. So 15 plus 6, 21 elastic constant. Okay, so for non-isotropic material are those material whose properties are directional dependent. Yani in x direction they have some other properties, in y direction they have some other elastic properties. Okay, and similarly in compression they have different properties, in tension they have different elastic properties. So those are known as non-isotropic material. Okay, so for non-isotropic material, the independent elastic components are 21. So you require 21 components to relate stress with strain. Okay, to relate stress with strain. Now, for isotropic material, a material like steel and many other material, the properties are not directional dependent, meaning the properties in x direction are same as the properties in the y direction and the properties in the z direction. Okay, directional, there is no directional dependency. Your properties are directional independent. If you just take a sample from a steel and you test it in any orientation, you should get same properties. If you are not getting same properties, then it means that the material is not isotropic. Okay, so for isotropic material, these 21 elastic component reduce to only 2 independent elastic components. Instead of 21, you required only 2 components. Okay, you have studied the relation between the normal stress and the normal strain, the shear stress and the shear. You are coming across only E, the modulus of elasticity, nu, the Poisson ratio, and G, the modulus of rigidity. Okay, so it seems that there are 3 elastic constants, because if you relate the sigma x with epsilon x, epsilon y, epsilon z, so you know the relation with the generalized form of the stress strain relation, so you know that they are related through E and nu. Similarly, this tau xy is related through G. Tau xy is equal to G gamma y. It's simple. Okay, it has nothing to do with the other elastic constant, with the other, this tau xy is not dependent upon epsilon x, epsilon y, epsilon z, nor it dependent upon gamma yz and gamma z. It's for the isotropic material. Okay, so it seems that there are three elastic constants: the modulus of rigidity G, the modulus of elasticity E, and the Poisson ratio nu. So these three elastic constants, but out of these three elastic constants, there is a relation between these three. And if you know any two of them, the third one is known to you. So it means that there are only two independent elastic components, elastic constants. So if you know two, then the whole story is known to you. You can convert stresses into strain, and similarly you can convert strain into stresses. Okay, so now you were using this relation in your mechanics of solid 1 in your chapter number 2 while calculating the shear stresses. So or from the strain or strain from the stresses, from the shear stresses. So you were using this relation. Okay, and you are not aware of the derivation of this relation. How this relation is what is the relation and how they are related to each other and what is the source of this relation. Okay, so now we are discussing this relation. How can we get this relation? Okay, this G modulus of rigidity is equal to E divided by 2 into 1 plus K. Okay, so now we are talking about this, how to get a relation between these things. So we talk about that there are 21 elastic constants for non-isotropic material, but for isotropic only 2 are required because the third one is related to the other 2. Okay, so to get a relation, let's consider a pure shear state of stress. So this is a pure shear state of stress. So tau is obviously the maximum shear stress. Okay, because there is the normal, the identity of the maximum shear stress is that the normal component on x and y are equal. So in this case they are 0, so mean equal. So this is the maximum shear, and this is a pure shear state of stress. Now using the stress transformation technique, you can convert this and you can get the principal stresses corresponding to this pure shear state of stress. Now if you draw the Mohr circle corresponding to this one, so let me draw the Mohr circle for this case C, which is sigma x plus sigma y is equal to 0, and R, the radius of this is equal to sigma x minus sigma y whole square plus tau xy whole square under the root. So it means that the radius of the Mohr circle is equal to tau. Okay, now if you draw the Mohr circle, so this is the Mohr circle. Okay, this is where the C is here located. Okay, the point, this point is what? This is tau comma 0. This is minus tau comma 0. I'm not writing it, and this is 0 comma tau, and this is 0 comma minus tau. Okay, so this is the principal stress. Okay, and this is the minus principal. The sigma 2 is minus tau and 0. Okay, so you know, if you just and this is your x-axis, because on the x-axis you have sigma x 0 and tau xy is tau, so this is 0 tau. Okay, so this is your x point. So this is the principal stress orientation. Here it is making 90-degree angle. So the actual principal plane will be located at an angle of 45 degree. So if you rotate this state of stress through 45 degree, so you will get what? You will get the principal state of stress. So corresponding to this, the principal state of stress is this one, where sigma 1 is tau and sigma 2 is minus tau. Okay, sigma 2 is minus tau. Okay, so now this is the case. You converted. So this rate of stress is equivalent to this rate of stress. Okay, these two are representing the same case. Okay, Okay. Now for this state of stress, the shear strain, which is actually the maximum shear strain. Okay. This is the maximum shear strain. So gamma is equal to tau divided by G. This is a well-known relation that the shear stress is related to the shear strain through this relation. This is a Hooke's law for shear stresses. And this is a biaxial state of stress. So for the biaxial state of stress, the epsilon 1 is 1 over E sigma 1 minus nu sigma 2. Since sigma 1 is equal to tau and sigma 2 is equal to minus tau, so this relation is converted to tau divided by E into 1 plus nu. So this is what this is epsilon 1. Similarly, epsilon 2 is minus tau divided by E into 1 plus nu. Okay. Now you also know that if the principal strains are known to you, then you can get the maximum shearing strain using this relation. Now this is also the maximum shearing strain here, okay, and the maximum shearing strain which you are getting from here will be same as the maximum shear strain if you are getting, because they are representing the same point. Okay, they are representing the same point. So the maximum shearing strain here in this case, this is the maximum shearing strain in this case, and the maximum shearing strain in this case is gamma maximum by 2 is equal to actually gamma by 2, because we are calling it just as a gamma by 2. So is equal to epsilon 1 minus epsilon 2 by 2. So gamma by 2, plug in the value of gamma, just relate this relation with this one. Okay, so just plug in the value of gamma from this equation and epsilon 1 and epsilon 2 from these two equations. So gamma by 2 is tau divided by 2 is equal to half of this one half of epsilon 1 minus epsilon 2. Okay, if you simplify this, so tau divided by E into 1 plus nu, tau will cancel with this tau. So you will finally get G is equal to E divided by 2 into 1 plus. Okay, G is equal to E divided by 2 into 1 plus. So this is the relation, and this relation, you got this relation from the stress strain transformation. Without the stress strain transformation, it is not possible to get this relation. Okay, it is not possible to directly get this relation. Okay, so this is the relation. So if modulus of elasticity and the Poisson ratio is known to you, then the modulus of rigidity is known. Okay, the modulus of rigidity is known. Now next, there is another term which is known as volumetric strain, which is also known as a dilatation. There is one is linear strain like epsilon 1, epsilon 2, and epsilon 3. And there is another strain which is known as volumetric strain, and volumetric strain is denoted by E, the word E. Okay, and what is volumetric strain? Volumetric strain is the ratio, is the change in volume per unit volume. Just like strain. Strain is change in length per unit length. So volumetric strain is change in volume per unit volume. And this is also known as a dilatation. So you know that for a, remember that you can represent any state of stress in terms of the principal state of stress. You should remember this. You can represent any state of stress in terms of the principal state of stress. If epsilon 1, epsilon 2, epsilon 3 are not known to you, yeah, sigma 1, sigma 2, sigma 3 are not known to you, then you can get it from the stress transformation relation, that you can get these principal stresses. Okay, so if principal stresses are known to you, this is a principal state of stress in which sigma 1, sigma 2, and sigma 3 are the principal stresses. So the strain corresponding to these principal stresses are epsilon 1 is equal to, this is a well-known constitutive relation, epsilon 2 is this one and epsilon 3 is this one. Now the length of this element in x direction is dx, in y direction is dy, and in z direction is dz. Now after application of stresses, obviously these lengths will change, and the new lengths will be the original length plus change in length. So dx plus epsilon 1 dx. Dx is the original length plus epsilon 1 dx, epsilon 1 change in length per unit length into the length will give you change in length. Okay, so this is giving you the length, the changed length. Okay, and similarly dy prime is equal to this one and dz prime is equal to this one. So you now know the changed length after the application of these stresses. Okay, now if you just calculate the change in volume, so change in volume, how can you calculate? आप में से ये माइक किसका ऑन है? साद इकबाल, साद इकबाल आपकी तरफ से डिस्टर्बेंस आ रही है. ओके, थैंक यू. अच्छा जी. So volumetric strain dilatation we are discussing. So the change in volume, the change in volume is the, this is the volume after application of the stresses, and this is the original volume. So this minus this will give you the change in volume, the change in volume. So just plug in dx prime is 1 plus epsilon 1, 1 plus epsilon 2, 1 plus epsilon 3, dx dy dz minus dx dy dz. If you multiply these three components, so you will get this one. This is the expanded form. If you multiply this with this one and then with this one, so you will get this one. Okay, so you are getting 1 plus epsilon 1 plus epsilon 2, epsilon 1 epsilon 2, epsilon 3 plus epsilon 1 3, epsilon 2 3, and epsilon 1 2 and 3. Now epsilon, which is a strain, and strain is a very small quantity, and the product of two small quantity you can neglect it. Okay, the product of two small quantity and even the product of three small quantity you can neglect that. They are those. So this you can make it 0, you can make it 0 0 and 0. So finally you are left with 1 plus epsilon 1 plus epsilon 2 plus epsilon 3 minus 1. So 1 will cancel with this one, so you will get the change in volume is epsilon 1 plus epsilon 2 plus epsilon 3 dV. dV is the differential volume of this differential element before application of the stresses. Okay, so now what is the dilatation or the volumetric strain? Change in volume per unit volume, per unit original volume. So the original volume is this one. Okay, so if you divide this with dV, so you will get epsilon 1, epsilon 2, epsilon 3. So what does it mean? It means that the dilatation, the volumetric strain, is equal to sum of the linear strain. The dilatation is equal to sum of the linear strain. So if you know the linear strain in all the direction, one may be positive, other one may be negative, but you will have to algebraically add them. An algebraic addition of those three components, linear strain, will give you the volumetric strain. Okay, will give you the volumetric strain. Now you can relate the dilatation or the volumetric strain with the principal stresses. With the principal stresses, if you just replace this epsilon 1 with its value in terms of the stresses, this is the relation in terms of the stresses, epsilon 2, and this is epsilon 3. So finally you will get this one. If you simplify this, add them with each other, so finally you will get 1 minus 2 nu divided by E epsilon 1 plus epsilon sigma 1 plus sigma 2 plus sigma 3. So this is what, this is the relation for the volumetric strain. Okay, this is the relation for volumetric strain. Any question from your side? Okay, now coming to another modulus of elasticity, another term which is known as a bulk modulus or volume modulus of elasticity. There is one modulus of elasticity which is E, which is linear modulus of elasticity. You can call it linear modulus of elasticity or one-dimensional modulus of elasticity. Now, if we are talking about the volume, so there is volume modulus of elasticity which is known as a bulk modulus. Okay, bulk modulus. So the bulk modulus is basically the ratio of a hydrostatic state of stress to the volumetric strain. If you have a state of stress in which all the principal stresses are same, and equal to sigma. Sigma 1 is sigma, sigma 2 is sigma, sigma 3 is sigma. Okay, so this kind of a state of stress is known as a hydrostatic state of stress. You know this, when all the stress components, all the principal stress components are same, then that kind of a state of stress is known as hydrostatic state of stress. So the ratio of this hydrostatic stress to the volumetric strain, which is E, and in the hydrostatic stress to the volumetric strain, this is known as a bulk modulus. For hydrostatic stress, sigma 1 is equal to sigma 2 is equal to sigma 3. So we know from the previous slide, this is E. E is equal to this one. So just you plug in the value of sigma 1, sigma 2 and sigma 3 as sigma. So this is sigma plus sigma plus sigma. So 1 minus nu divided by E into this one. So this is 3 sigma. So if you simplify this one, so you will get K, plug in the value, this value E and the sigma will cancel. So you are left with E divided by 3 into 1 minus 2. So this is what? This is bulk modulus. Okay, so the bulk modulus is related to the modulus of elasticity and the Poisson ratio. And it should be, because the volume, this is related to the volume changes, and the volume changes is dependent upon the modulus of elasticity and the Poisson ratio. Okay, so K is equal to the bulk modulus is equal to this one. Okay, now this equation is giving us a lot of information, and this is giving us some boundaries of the Poisson ratio. Okay, some boundaries of the Poisson ratio. Now, for most metal, we know that the Poisson ratio is around 1 divided by 3. 0.3, 0.33, this is the value, 0.29, 0.28, 0.3, 0.33, 0.31, 3233. So this is the usual range for most of the metal. Okay, so for nu is equal to 1/3. If you plug in this equal to, so this will be 2 into 1 by 3. So this is 1 minus 2 by 3 is 1 by 3. 3 will cancel with 3 1. So you are left with K is equal to E. So the bulk modulus is equal to the modulus of elasticity of the metal. Okay, K will become equal to E. For what? For most metals. Okay, for concrete, we take the modulus of elasticity equal to 0.25. Okay, for masonry, we take it between 0.25 and 0.2 and 0.25. So different materials have different Poisson ratio. Okay, but for metal, the bulk modulus is equal to E. Not for all material. Okay, only for metal. For most metal, the bulk modulus is equal to the modulus of elasticity. Now, there is another information from this equation. If you look to this one, and if you make this equal to 0, this term 1 minus 2 nu equal to 0, what will happen? K will become infinity. What does it mean? K infinity. Yani the bulk modulus will become infinity. What does it mean? It means that there will be no volume change. Okay, infinity means a stiff. If you have modulus of elasticity like infinity, and if you are applying a load on this, so what will happen? There will be no change in length, because its modulus of elasticity is infinity. Okay, so similar is the case for the bulk modulus. If the bulk modulus is infinity, which is not practically possible. Okay, now this is just a theoretical discussion. Okay, so when this term is equal to 0, when will this term equal to 0? When nu become equal to 1 by 2. When nu become equal to 1 by 2, so this is 1 minus 2 into 1 by 2, 1. So 1 minus 1 is equal to 0. So when nu become Poisson, when the Poisson ratio become equal to 1 by 2, so the bulk modulus will be infinity. Okay, so it means that the value of nu should always be less than 1 by 2 or 0.5. 0.5 से कम होनी चाहिए. एक boundary आपको जो है वो मिल गई, ठीक है? Poisson, you got a boundary for the Poisson ratio, upper boundary, that the value of the Poisson ratio cannot be greater than 0.5. It should always be less than 0.5. Why? because for corresponding to 0.5, the bulk modulus is infinity, which is not practically possible. In this universe, each material have some modulus, some bulk modulus it should have, which will be less than the infinity, okay, and it will deform. There will be volume changes if you apply some load on them. Okay, there must be some volume changes, okay, when you apply some load on this. Okay, so you have this case that the bulk modulus cannot be infinity, so the upper boundary of this is 1/2. It cannot be 1/2, it should be less than 1/2. Okay, so this is one thing. Now the other thing is that you can have any value of nu which is greater than 0. Okay, you cannot have a negative value of the Poisson ratio. We'll discuss there is one material for which we have a negative value. Okay, but that is an exceptional case. We will discuss it after this. But what does it mean? What is the meaning of a negative Poisson ratio? The negative Poisson ratio means that if you are pulling a certain material, if you are applying a tensile force on that material, so there will be elongation, and the other direction will also increase, which is not the usual observation for the common material. In the case of common material, if you are elongating a certain material in one direction by applying a tensile force, then the other direction will get reduced. Okay, so this is usual observation for common material. Okay, so its value cannot be negative for common material. Okay, so its value should not be equal to 0. It should be there must be some change if you are applying a force, so there must be some change in the other direction, so it cannot be 0, it should be greater than 0. So there are two boundaries for the Poisson ratio, that the value of Poisson ratio should be in between 0 and 0.5, not 0 and not 0.5. Okay, for common material. So this is the usual range you got it, and this is from the mechanics that you got the two boundaries of this, and this is the requirement of the mechanics. Okay, now there is there are a set of materials in which there is a negative Poisson ratio concept, meaning that if you are applying a tensile force, there will be elongation in that direction, but there will be elongation in the other two directions also. And this is the requirement of its crystalline structure. Its crystalline structure is of such a kind that it remains its shape. Okay, let's suppose if the crystalline structure is like a cube. Okay, so if you are increasing the one direction of the cube, so it will become a cuboid, but the other two direction will automatically increase such just to remain it as just to keep its cube shape. Okay, so that's why its Poisson ratio is negative. Okay, now you can you define any one of you can define the Poisson ratio? आप define कर सकते हैं, कोई भी आप में से define करे जरा Poisson ratio को, any one of you? Unmute करके बता.
Ratio of lateral strain to longitudinal strain.
Okay, lateral strain to the longitudinal strain. Okay, but there is another thing, which is mu is equal to, it is the negative ratio of lateral strain to the longitudinal strain, the axial strain, I'm sorry. Okay, this is lateral strain to the axial strain. This is known as, this is the negative ratio, because for this ratio is always, this ratio is always a negative number. If you are getting elongation in the axial direction, there will be shortening in the lateral direction. And if you are getting shortening in the axial direction, there will be elongation in the lateral direction. Okay, so it means that this ratio will always be negative for common material. Okay, so that's why this negative sign appears, that to make this Poisson ratio as a positive number, because you know that when E is specified, the Poisson ratio is specified, it is said that the Poisson ratio is 0.3. It is not said that it is minus 0.3. Okay, it is 0.3 because the number is a positive number, so that's why Poisson ratio, it should be defined, it is the negative ratio of the lateral strain to the axial strain. It is the negative ratio. Negative mean negative will become a positive number. Okay, so this is the usual case. But if you have such a material that if when you are applying an axial elongation, so the lateral will always be positive, will also be positive. So what will happen? This will become a positive number, and if you multiply this, so you will get a negative number, so a negative Poisson ratio. Okay, such kind of a material are piezoelectric material. They are special kind of a material, piezoelectric material. Piezoelectric. They have some special properties, and that's why they are very useful in measuring devices. They are very useful in measuring devices like accelerometer, just to measure acceleration and in structure or the acceleration of the ground. Okay, so these kind of material are used in those. So we do have in our earthquake engineering center, we do have piezoelectric accelerometer. Okay, piezoelectric. So piezoelectric material, so those material are having the negative Poisson ratio. Okay, are having the negative Poisson ratio. This is exceptional case. Negative Poisson ratio mean when it will be less than 0. Okay, so when one direction is elongated, so the other two directions will also elongate. Okay, so this is the discussion about the modulus of the bulk modulus, the volume modulus of elasticity, and these things. Okay, now let's have an example. You have a block. This is a block. Okay, and this block is having dimension. This is 4 inches. Okay, let's suppose this is B is 2 inches, and this is C is 3 inches. Okay, these are the dimension of this block, and this block is subjected to a uniform pressure from all the sides. Okay, this is subjected to a uniform pressure from all the sides, and the magnitude of pressure is P is equal to 20 psi. Okay, so like this is submerged in water where the pressure is 20 psi. This block is submerged in water where the pressure is 20 psi. Determine dilatation, bulk modulus, and the change in length of each size. Take E modulus of elasticity equal to 600 psi and the Poisson ratio equal to 0.4. Okay, so this is the case. Now in this case, since this is submerged in water, so there is equals the state of stress is hydrostatic state of stress. Okay, so the principal stresses from all the direction will be equal to the pressure. Sigma 1 will be equal to sigma 2, sigma 3 equal to minus 20 psi, since this is compression. Okay, uniform pressure, so pressure is a compressive force if it is applied on a body from all the sides. Okay, now we have the equation of dilatation, E equal to 1 minus 2 nu divided by E sigma 1, sigma 2, sigma 3. So this is the relation 3 sigma. So let's plug in the value. So you will get minus 0.01. Okay. The unit of this minus mean there will be reduction in the volume. Since this is subjected to a compressor stress, to a pressure, so obviously there will be reduction in the volume of this block. Okay. There will be reduction in the volume of this block, and E equal to this minus 0.01. Minus 0.01. What is the unit of this? So this is volumetric strain. So strain has no unit, but sometimes we say with the linear strain, we say inch per inch. We say millimeter per millimeter. So in this case, we can say cubic millimeter per cubic millimeter. Okay, or you can leave it without any unit. Okay, so minus 0.01. Now, what will be the change in volume? Let's suppose if you know the volumetric strain, then what will be the change in volume of this block? So let's calculate the change in volume. So how can we calculate the change in volume? If you just multiply this with the volume of the element. Now volume of the element is 2 into 4 into 3. So this is 24. Okay, 24. If you multiply this with 0.01, so you will get 0.24. So the volume of this is how much? 24 cubic inches, and there will be a change in volume of 0.24 cubic inch when you apply this 20 psi of stress. Okay, hydrostatic stress. The bulk modulus, which is what the bulk modulus is, the hydrostatic stress, and you can get it simply by 20 divided by this. Okay, the hydrostatic stress divided by the dilatation. There is a relation available. So if you 20 divided by 0.01, so you will get what? You will get 2000. There is a relation that E divided by 3 into 1 minus 3 nu. So this is 2000 psi. So its bulk modulus, its modulus of elasticity is 600, but its bulk modulus is 2000 psi. Okay, and the next thing is that the change in length of each side. Okay, so since this is a hydrostatic state of stress, so the strain in each direction will be same. So that strain is epsilon is equal to 1 over E sigma 1 minus nu sigma 2 plus sigma 3. So sigma 1, sigma 2, sigma 3 are equal to sigma. So this is equal to this one. So you will get the strain in all the three directions are minus 0.00333. Okay. So this is the strain. Now the change in length of each side, the change in length, you can get it strain into the original length. Change in length of side A is equal to strain into the original length of strain into 4 is equal to this one. Change in length B, strain into B, which is equal to this one, and strain in C is equal to this one. Okay, so this is what this is, the change in length of each side. Change in length of each side. Okay, 0.01 inch, 0.00667, and 0.01 inch. So these are change in length of each side. Okay, so this is a problem related to the elastic transfer. Any question? Okay. Now, before going to discuss the theories, now let's first discuss the concept of strain energy. The concept of elastic strain energy. What do we mean by the strain energy? Now, when you apply load to a body, stresses and strain will be induced in the body. Okay? When you apply force on a body, so the body, there will be stress and strain induced in the body. And due to this straining motion, the strain is like a deformation. Okay, so this deformation, when there is a force and there is a deformation, so force times the deformation or the displacement is a work done. And this work done is stored in a body as a strain energy. Okay, so the work done on a body by the external agency is stored in the body as a strain energy. When you apply a force, so there must be some deformation. So force times the deformation will give you the work done, and this work done is stored in a body as a strain energy. And if the body remain elastic, as we have discussed here, that this is when an elastic body, it is not exceeding the elastic limit, so that energy is known as the elastic strain energy. Okay, the elastic strain energy. Now, if you have a body which is subjected by a force P, and the deformation in the body produced in the direction of P. Okay, this is the deformation produced in the direction of P is equal to delta L. Delta L is the displacement or the deformation produced in the direction of P. Okay, so delta L, so if you draw a graph between the change in length and the applied force, so you will get a straight line because the body is elastic. Okay, so as you are increasing the deformation or the load, the deformation get increased. Okay, so if at a certain limit the load is P, at a certain point the load is P, and the deformation is delta L, then what is the work done? Since this load is applied steadily, okay, we are assuming that the load is applied steadily. Steadily mean that you are applying, not applying the load, all of the load suddenly. Our assumption is that the load is applied steadily, that you are applying load starting from 0 and then increasing it up to P. Okay, so you are gradually applying the load from 0 up to P. So the displacement will also gradually increase from 0 to delta L. Okay, so the work done here is equal to, since we have the definition of the work done is P into delta L. But since in this case, this is not a sudden load that you are applying a load and there is a deformation delta. Okay, that for this whole delta, if this load is constant, then it will start from here and it will bring it to this position. But this is not the case because you are applying the load gradually and increasing it to P. So in this case, the work done is equal to this triangle. The area under this curve, this is a load deformation curve. This is load deformation curve. So this area is half of P into delta L. Now from the stress strain relation, you know that P is equal to sigma dA, sigma A, and strain, so the change in length is epsilon into L. So if you plug in, replace P and delta L with this and this one, so you will get this half of sigma into epsilon into AL. Now what is AL? AL is the volume of, if you have, let's suppose if this is an axially loaded member, okay, axially loaded member having a length L and cross-section area A, so AL is the volume of this member. Okay, so if you just bring this volume to this side, so this is energy per unit volume. When energy per unit volume, which is known as a strain energy density, or simply it is known as energy per unit volume, it is represented with small u. Okay, it is represented with small u. So small u is equal to half of stress into strain. Okay, half of stress. So energy per unit volume is equal to half of stress into strain. And if you draw a graph or a stress strain curve for the up to the elastic limit, so up to the elastic limit it is a straight line. Okay, so up to the elastic limit it is a straight line. So this, if this is the strain and this is stress, then this area is known as what? This is the elastic strain energy per unit volume. Okay, this is the total elastic strain energy, and this is the, if you have a plot of the load versus deformation. But if you have a plot of the stress versus strain, then this is giving you energy per unit volume. Okay, so energy per unit volume by definition is half of stress into strain. This definition also holds good for shear also. Half of tau into gamma. Yeah, half of tau into gamma. So that will give you the energy associated with the shear stresses. This is energy associated with the normal stresses. Okay, so now if we use the Hooke's law, so U is equal to half of sigma into E is equal to half of sigma, and if I replace this epsilon from the Hooke's law for a one-dimensional state of stress, so this is sigma divided by E, so this is equal to sigma square divided by 2E. So this is, if you just omit the strain component, so you can get the strain energy from this one. So if the stress is given to you, then stress square divided by 2E, the modulus of elasticity. Okay, so this will give you strain energy per unit volume. Okay, this will give you strain energy per unit volume in a body. This concept of the energy is required for the analysis of structure, for the structure analysis method, for calculation of the deformation. Okay, you will study the structure analysis 1 course, and in structure analysis 1 you will study this strain energy method. Okay, how to get, you have studied the double integration method, the area movement method, the conjugate beam method.
but you haven't studied the energy method, how to get deformation using the energy method, how to get solve a structure using energy method. So energies are very important, so you should know the basic concept of the energy. So this is an expression, this one are the expression for energy per unit volume. Okay. Now the total strain energy, as I have told you, that you can represent any state of stress in terms of the principal strain and principal stresses. Yeah, you can represent any state of stress. So if you have a state of stress, and if you just convert that state of stress into the principal stresses, and those principal stresses are sigma 1, sigma 2, and sigma 3, then the energy, the total, since this is this relation, we got it for a uniaxial, for one-dimensional state of stress. But if you have a three-dimensional state of stress, okay, so in that case, the total strain energy, because these are principal stresses, are giving you the total strain energy. So because they are representing this sigma 1, sigma 2, and sigma 3 also represent the shear component also. Okay, so the total strain energy in this case is equal to half of sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. So if you plug in the value of epsilon 1, epsilon 2, and epsilon 3, this is and multiply this sigma 1, so you will get these component. And if you simplify this one, so the total strain energy expression is sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu sigma 1 sigma 2 sigma 2 sigma 3 and sigma 1 sigma 3. Okay, so this is the total strain energy per unit volume for a three-dimensional state of stress. Okay, this expression is the expression of the total strain energy. Now, the strain energy may be divided into two components. One is the energy associated with volumetric changes, meaning dilatation, and the other is the energy associated with the shear distortion. The linear strain tries to change the change the volume of the body, and the shear strain, they distort the body, they produce angular deformation, and they change the shape of the body without changing its volume. They are not changing the volume of the body, the shear stresses and the shear strain. You are not changing the volume of the body, you are only distorting the body, they are changing the shape of the body. The linear strain change the shape of the body, the volume of the body. Okay, so you can divide them into two components because they are separate definition of them is very important, because we need this energy separately, because some phenomena are related to them separately. Now, the energy which is associated with the volume changes is known as the dilatation strain energy. And how to get the dilatation strain energy? So since dilatation strain energy is associated with the volume change, so this kind of energy may be obtained if you subject the element to an average stress, and whose value will be sigma 1 plus sigma 2 plus sigma 3 divided by 3 in all the three directions. So this is a hydrostatic state of stress. Okay, so if you are applying this sigma 1, sigma 2, sigma 3, so not only they will change the volume of the body, but they will also distort the element. But if you have a hydrostatic state of stress, so there will be an effect of sigma 1 on the volume change, the effect of sigma 2 on the volume change, and the effect of sigma 3 on the volume change. But if you just apply average of these on the three, so the total volume change will be same. Okay, the total volume change will be same. So this is sigma 1 plus sigma 2 plus sigma 3 by 3. So in all the three directions, so U dilatation is equal to, from this relation, sigma 1, sigma 2, sigma 3, all of them is equal to sigma average. So if you plug in the value, so you will get 3 into 1 minus 2 nu divided by 2e into sigma average square, and again replace sigma average with sigma 1 plus sigma 2 plus sigma 3 by 3. So finally you will get the dilatation strain energy, or the energy associated with the volume change. energy associated with the volume change is equal to 1 minus 2 nu divided by 6c sigma 1 plus sigma 2 plus sigma 3 square. कुछ समझ में आ रहा है कि नहीं? चीजें जो है वो आप न दोबारा जो है वो लेक्चर को देखते हैं, आप चीजें बहुत लाइट जो है वो ले रहे हैं, ठीक है ना, चीजें लाइट ना लें, ठीक है ना। ये आपका जो है वो आपके लिए, मैं तो बार बार बताता हूँ कि मैकेनिक्स जो है और मैकेनिक्स ऑफ सॉलिड बेसिकली जो है वो इज एक बेसिक जो है वो कोर्स है जो कि आपके इंजीनियरिंग का पूरा बेस जो है वो बना है, ठीक है ना। आपका जो भी एरिया आप ले लेना, चाहे आप मैकेनिक्स ऑफ सॉलिड यानी स्ट्रक्चर एनालिसिस, स्ट्रक्चर डिजाइन के कोर्सेज जो है वो ले लें, या इवन जो है वो हाइड्रोलिक्स के जो है वो कोर्सेज आप ले लें, या इवन सॉइल मैकेनिक्स के कोर्सेज ले लें, या मैकेनिक्स हर जगह घुसा हुआ है, ठीक है ना। एंड यू डू हैव द बेसिक कॉन्सेप्ट जो है वो क्लियर, ठीक है ना। वो अगर आपका क्लियर जो है वो नहीं है, सो देन यू हैव अ बिग प्रॉब्लम इन योर इंजीनियरिंग जो है, ठीक है ना। आप एक अच्छे सुपरवाइजर बन जाएंगे, बस वैसे जो है वो साइन वाइन करेंगे, दस्तखत करेंगे, और कुछ जो है वो आपका नहीं होगा। यू विल नॉट जी जी। एनी प्रॉब्लम?
No, sir, I speak English. I speak
हाँ?
Urdu.
आप
You are speaking Urdu, that's why I'm saying, sir, speak
I
English.
cannot hear you properly. Speak loudly.
सर वही इंग्लिश की हुआ है सर, उर्दू की वो है।
Okay. Okay, so this is the energy associated with volume changes. Now coming to the distortion energy. So one procedure is that if you subtract, this is total energy minus this dilatation energy will give you what? Will give you the energy associated with distortion, because here these are the two sources. One is the volume change, the other one is the distortion. If you just subtract this minus this, u total minus u dilatation will be equal to this distortion energy UD. But I'm getting this expression using another approach, and that approach is directly from the energy associated with the shear deformation. So the energy associated with shear deformation, which is known as a distortion energy, and for a three-dimensional state of stress, the maximum in-plane shear stresses are in the 1, 2, this is sigma 1 minus sigma 2 by 2. In the 2, 3, this is sigma 2 minus sigma 3 by 2. And in the 3, 1, sigma 3 minus sigma 1 by 2. These are the three shear component in the three-dimensional state of stress. Now, the energy associated with the shear deformation, the distortion energy, is equal to, we know that for a unidirection, this is half of sigma into E. Epsilon, I'm sorry. So this is for the shear, this is half of tau 1 2 into gamma 1 2 plus tau 2 3 into gamma 2 3 plus tau 3 1 into gamma 3 1. So just plugging the value of this gamma 1 2 is equal to tau 1 2 by g, and similarly the other two. So you will get 1 over 2g tau 1 2 square plus tau 2 3 square plus tau 3 1 square. Now plug in the value of tau 1 2, tau 2 3, and tau 1 3 in this equation. So you will get this plus this square. Okay, so just open these squares. Okay, so you will get this one, and then simplify, just cancel some of the components and add some of the components. So you will get this relation. Okay, so this is the final version of this relation, that 1 over 4g into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. So this is an expression for the distortion energy per unit volume in a three-dimensional state of stress. Okay, now if you want to get a relation for the two-dimensional, so in the case of a two-dimensional state of stress, so if you plug in sigma 3 equal to 0 in this expression, okay, so the distortion energy is equal to distortion energy per unit volume is equal to, just make this equal to 0, this equal to 0, and this equal to 0. So you are left with this one. Okay, and for uniaxial state of stress, just make this and sigma 2 equal to 0. So this is and this is equal to 0. So sigma 1 square divided by 4g. So this is for a uniaxial state of stress. Okay, uniaxial state of stress. So this is expression. So you can get this expression if you subtract this from this. Okay, ut minus u dilatation, you will get the same expression, this one. Okay, so this is the case. Now this is all about the strain energy. So we in the strain energy we talk about the total strain energy, and we talk about the energy associated or the dilatation strain energy, and we talk about the distortion strain energy. And the other concepts are not related to the failure theory. The only concept which is the distortion energy, which is related to one of the theories. So we'll require these three questions, 1, 2, and 3 questions, or especially these two equations, because we'll discuss the two-dimensional state of stress. So we'll require these two cases. Okay. Now, theories of failure. Now, what are theories of failure? Give me just a minute. मैं जरा पानी पीता हूँ, 1-2 मिनट मुझे जो है वो लगेंगे, आप जरा
Okay, ji. Can you hear me? Okay. पता नहीं ये मेरी माइक कमजोर है कि क्या वजह है, आपकी आवाज सबकी मुझे बहुत स्लो आ रही है, हालांकि मेरा वॉल्यूम चेंज वो पूरा जो है वो अप्लाई किया हुआ है। ओके जी, सो फेलियर थ्योरीज, जस्ट अ मिनट यार। Okay. When an engineer is faced with the problem of design using a specific material, it becomes important to place an upper limit on the state of stress that defines the material failure. Okay, if you are designing something, then you will have to say, you will have to keep the stress within certain limit. Okay, and this is what design means. Okay, you will have to proportion the geometry, and you will have to select such a material that you will have to keep the level of stress within certain limit. Okay, just to avoid the material failure. If the material is ductile, failure is usually specified by the initiation of yielding. Okay, for ductile material, failure means yielding. Okay, one thing. Whereas if the material is brittle, it is specified by fracture. Okay, so for brittle material, failure means fracture. For ductile material, failure means yielding. For brittle material, failure means fracture. Now you will have to define, any one of you will have to define what do we mean by the ductile material and the brittle material. Any one of you. किसी को पता है मैसेज?
सर डक्टाइल मटेरियल ऐसा मटेरियल होता है सर जो मतलब हमें मतलब ग्रेजुअली इसमें चेंज आता है सर, इसके मतलब एकदम वो नहीं टूटता, इसके मुकाबले ब्रिटन मटेरियल एकदम टूटता है सर।
एकदम टूटता है। So he is saying that ductile material is such a material which gives you warning before its failure. So the failure is not like a sudden failure, it fails gradually. While the brittle materials, it may give you a higher strength, a brittle material may give you higher strength, but its failure will be sudden. It will not give you any warning. Okay, like if you have a ductile steel and if you are applying a tensile force, so you will be able, you can readily define that now after some time it will fail, so you can have some times for preparation, just to do some preparation. So maybe in the case of a ductile material, you can get a warning of years that let's suppose if there is some deflection in your roof slab, then you say that okay, it may fail after 10 years. So you can have sufficient time just to do preparation and to do something for that case. Okay, so this is the definition of a ductile material. But a brittle material will not give you, if you are testing a brittle material in the universal testing machine, so you will apply and it will take load, and all of a sudden it will fail without giving you any appreciable deformation, appreciable warning. Okay, so the material which is ductile, its failure is defined by yielding, and when the material is brittle, its failure is defined by fracture. These mode of failures are readily defined if the member is subjected to a uniaxial state of stress, just like in the case of test. Okay, if you have a uniaxial state of stress, then you can say that if I'm applying this much of a tensile force, then you can relate it directly. Okay, the uniaxial state of stress, you can relate it directly to the experimental result, because you will have to, on material, you will have to perform the experiment. Okay, if you want to know the yield strength of the material, and if you want to know the fracture strength of the material, you will have to perform the test.
But if you are designing, so in the case of design, you are not performing tests on each and every component of the structure. Okay, so you are designing it based on the experimental result. Okay, then how to compare that actual condition your design with the laboratory result? This is the work of failure theory. Okay, or the actual body or actual design structure, if you want to compare it with the experimental result. So this comparison is made by various failure theories. Okay, it is not in the case of a uniaxial, because the test is performed in a uniaxial in a simple tension environment. The test is what? In a simple tension or simple compression. The concrete cylinders are tested in a simple compression environment, and the steel is tested in a simple tension environment. But in the actual field condition, the body may be subjected to a biaxial and triaxial state of stress. Okay, like in the case of a beam. In the case of a beam, so in the case of a beam, you have a biaxial state of stress. Okay, in the case of a three-dimensional body, you have a triaxial state of stress. Okay, so these modes of failure are readily defined if the member is subjected to uniaxial state of stress. Why? Because the test is uniaxial and the actual case is uniaxial. Okay, so it's very easy, as in the case of a simple tension. However, if the member is subjected to biaxial or triaxial, the criteria for failure becomes more difficult to establish. It's not easy, because how to relate if, let's suppose if you have a biaxial state of stress in which one is the compressive stress, the other one is the tensile stress, and there is a failure in the tensile direction. So how can you relate it to the field condition or to the laboratory test? Because the laboratory test, there is no other direction stress. Okay, so this is what is the need of these failure theories. Okay, so various theories of failure exist which relates the test results performed in uniaxial direction to the biaxial and triaxial state of stress. Uniaxial direction performed in the laboratory, and biaxial and triaxial are the actual tests. So this is the work of these theories. So various theories exist. No single theory, however, can be applied to a specific material at all times. One thing, when there is one statement that should be added here, that different theories exist for brittle and ductile material. Okay, a theory which is applicable to the brittle material may not be applicable to the ductile material, or the theory which is applicable to the ductile material may not be applicable to brittle material. Okay, so but there is another boundary that no single theory, however, can be applied to a material at all times. Why? Because the behavior in either may be either ductile or brittle depending upon temperature. A material at low temperature can behave in a brittle manner, and at high temperature it can behave in a ductile material. Of steel ko garam, and when you just heat up steel, so it become more ductile than when it is become, and if you just cool a certain material, so it become more brittle. Okay, so temperature, rate of loading, this is another thing. Rate of loading is also important. For each loading, in the loading protocol, if you are performing a tension test in the universal testing machine, so the loading protocol is mentioned that you will have to apply loading at a certain rate. If you are applying load at a faster rate, then the material may behave as a brittle material. And if you are applying the load at a slower rate, then the material may behave as a ductile material. Even if you have a ductile material like a steel, and if you are all of a sudden applying the load, so there is no chance for the material to yield. So it will, the load is such a high rate that it will behave like a brittle material. Chemical environment, okay, in certain chemical environment, certain material behave like a brittle material, and another chemical environment means like if you have a saline water, and if you just submerge a material in this, so it may behave differently if you just test this material in or if you just load this material outside the saline water. Okay, so this is the chemical environment, or the way the material is shaped or formed. Different shape of the material may give you, if you shape it in one shape, it may behave like a ductile material, and in another shape, it may behave like a brittle material. So you will have to check a material based on both the if the material is subjected to this kind of environment. Okay, if the temperature variation is very high, if the rate of loading is like very high or very low, both kind of loading, if there is any chemical environment, or if the shape is different, then you will have to. But if the change is not, if these things do not exist, then you can apply a single theory or a single, you can apply the theories for ductile material to the ductile material, and theories for brittle material to the brittle material. Okay, so there is no need to design it for both ductile and brittle theories. When using a particular theory of failure, it is first necessary to calculate the normal and shear stress at points where they are the largest in the member. So how to use these theories? Okay, any one of the theory. You will have to define the state of stress and the critical state of stress, because if you have a body, and at that body you may have variation in the stresses, just like in the case of beam, you have variation in the stresses along the length of the beam. So you will have to select the critical locations, and at the critical location you will have to define the state of stress. Okay, so once you get the state of stress at that point, then you will have to convert that state of stress into the principal state of stress, because all the theories, they are based on the principal stresses. Okay, so convert that state of stress into the principal state of stress, and then apply those theories. Now let's discuss some of the theories. Okay, the first theory is the maximum shear stress. The theory results from the observation that a ductile material slips occur during yielding along critically oriented plane. You might have observed this in your tensile test in your mechanics of solid 1 late course. Okay. When you perform a tension test, what happens in a tension test of a steel bar? First, when you apply a load and you are gradually increasing the load, so what happens? First, there is a neck formation. And after neck formation, there is fracture. But that fracture is basically not perpendicular to the axis of the member, that is inclined to the axis of the member. Have you observed this thing? Observed किया आपने experiment किया ना?
Yes.
Okay. So
Yes, sir, किया था.
So the plane of failure is not perpendicular to the axis of the member or to the direction of the load. Usually for brittle material, it is like perpendicular to the direction of the load. Okay, but for ductile material, if you observe, then that is usually at 45 degrees. And this is what is the observation, and this observation was made, and based on this observation, this theory was presented. Okay, so when you observe, so in different experiments they observed, and they observed that there are some critical plane and there is a slippage. Basically, when there is a neck formation, so there is a slip along this plane. So this slip is basically responsible, and slip is what? The shear strain. So there is a shear stress along this slip plane, so which exceeded its capacity, and then there is a failure due to the shear strain. Okay, so this suggests that the maximum shear stress plays the key role, and it is assumed that yielding of the material depends only on the maximum shear stress that is attained within an element. So what is this theory suggesting? This theory is suggesting that you will have to not look to any other thing, you will have to look to the maximum shear stress. Okay, you will have to look to the maximum shear stress, and you will have to keep a control on the maximum shear stress. Forget about all other stresses, because there will be a normal stress, there will be normal stress in one direction, there will be normal stress in another direction, and there will be shear stress in one plane and shear stress in the other plane. And there are some other quantities also. There may be energies. So, but you will have to look only to the maximum shear stress. Okay, and you will have to keep an eye on the maximum shear stress. And according to this theory, failure will commence when maximum shear stress in a body reaches its maximum stress as a reading of the specimen. So what this theory is doing, this theory is comparing this case with this case. This is a laboratory experiment. When you perform a test in the laboratory, so you perform like a uniaxial state of stress. So this is the state of stress. Okay, you are applying stress in only one direction. So you calculate the yield strength, that is when you perform the test. So that is very easy to define the yield stress. If you have a stress strain curve, then you can easily define the yield strength of the material. So you can have this yield strength. Okay, so if you convert this unidirectional state of stress to this one, there are some component also here. Let me show those one. There must be some normal component here also. Okay, some normal components. Okay, because on the maximum shear stress plane, the other two plane may have some values. Okay, and those values are equal in magnitude and in sense also. Okay, so this is, if you convert this state of stress using the Mohr circle, so you will get this state of stress, and this is the maximum. If you have a uniaxial, so at 45-degree angle, you have a maximum shear stress. So this is the critical shear stress. This is the critical shear stress. So the critical shear stress in a lab environment is sigma yield point by 2. You can get it if you get the yield strength of the material. So the critical shear stress at the time of yielding is sigma yield point by 2. So this is basically the yield shear strength. This critical shear strength is the yield shear strength of the material. Now for a two-dimensional state of stress, the maximum shear stress, the absolute maximum shear stress, is the maximum of these three. So what this theory is saying, that failure will initiate when maximum of this become equal to this one. Okay, when there will be one maximum, either this will give you maximum if they are of different sign, or if they are of the same sign, then this or this will give you the maximum value, but any one of this maximum value. So you will have to compare this with this one, sigma yield point by 2. Sigma yield point you will get from the experiment, okay, from the simple tension test. So compare this, and if this is equal to this one, so this will make the initiation. If this is less than this one, so this is safe. If this is greater than this one, then this is the failure condition. जब ज़्यादा हो जाए, when it exceed this value, so this is the failure condition. Okay? So let's do it. Let's develop some equation. So according to this theory, sigma 1 minus sigma 2 by 2 should be less than this one thing. Sigma 1 by sigma 2 should be less than this one, and sigma 2 by sigma 2 should be less than this one. If you just remove this modulus sign, so you will have to have a plus minus sign. And if you just bring it to cancel this 2 with this one and bring it to this side, so sigma 1 divided by sigma yield point minus sigma 2 by sigma yield point should be less than or equal to 1. Similarly, sigma 1 by sigma yield point should be less than or equal to 1. And similarly, this should be less than or equal to 1. At the commencement of failure, when just the failure starts, so this will become equal to this 1. This should be equal to this one. This should be equal to 1. So these are the at the yielding, this will be the value. So these are the 6 equations. Either this will give 1, or this will give 1, or this will give 1. But if you plot these 6 equations, okay, this is with plus 1, you will get this line. This equation with minus 1, you will get this line. This equation with plus 1, you will get this line. This equation with minus 1, you will get this line. This equation with plus 1, this line. and this equation with minus this sign. So you will get this six-sided figure, which is not a hexagon but six-sided figure. So this six-sided figure is basically giving you the boundaries, the failure boundary according to the maximum shear stress theory. The theory is very simple. Okay, the theory is very simple. Calculate the maximum shear stress, the absolute maximum shear stress. You can do it using this expression. You have the state of stress given. Just calculate this, and take the maximum value. So that will give you the absolute maximum. Okay, and compare this with this one. Okay, so if it is less than, so it's okay, greater than. But this is graphically just to compare various theories. So I'm just also showing these theory graphically. Okay, so this is a plot between sigma 1 by sigma yield, and this is sigma 2 by sigma yield. So this is according to the maximum shear stress. Okay, so any point inside this, if you have, let's suppose if you calculate sigma 1, sigma yield will be given to you, sigma yield point, and if you have sigma 1 and sigma 2 given to you, just calculate sigma 1 by sigma yield and sigma 2 by sigma yield and locate a point on this. This is a Cartesian coordinate system. So let's suppose if the point is here, this is safe condition. If the point is here, safe condition. But if the point is here, it is failure. Even if the point is here, this is also failure. This boundary also belong to the failure, initial of the failure, initiation of the failure. Okay, so this is the case. So when you plot these equations, so you will get this case. Okay. Now, the next theory is the distortion energy, which is also known as the Mises theory, and a well-known and most widely used theory for ductile material. Most widely used theory for ductile material. This theory is also applicable to ductile material and is based on the distortion energy stored in a stress element due to the shear deformation. According to this theory, the statement is what? You have the two conditions. This is laboratory condition and this is the actual stress condition. Okay, this is the actual stress condition. As I've told you that to apply the theory, you will have to first get the state of stress at the critical location, and then you will have to convert the state of stress into the principal state of stress, which is this one, and then you will have to compare this with this one. So the comparison is according to the distortion energy. You will have to compare the distortion energy in this case with the distortion energy in this case. Okay, and then you will have to make a relation. Okay, so failure commences when the distortion energy in a body reaches the distortion energy at yielding of the specimen in a sample tension test. When distortion energy in this reaches the distortion energy in this case. Okay, this is this theory. Okay, so at the yielding, the distortion energy in this case, as we know, let me show you the previous the distortion energy equation. This is for uniaxial direction. This is for biaxial direction. So for uniaxial direction, this is yield. This is for the laboratory test. So this is now the case. Sigma yield, sigma 1 square by 4g. So sigma yield point square by 4g. Okay. This is what this is for this case. This is the distortion energy stored in this case. Okay. Now for a two-dimensional case, for this case, the distortion energy is this one. We know this. Okay. Now at yielding, this should be equal to this one. This should be equal to this one. So just this one. 4g will cancel with 4g. Just bring this to this side. So this is sigma 1 by sigma yield point square plus sigma 2 by sigma yield point square minus sigma 1 by sigma yield, and sigma 2 by sigma yield is equal to 1. This is what this is equation of ellipse. And this is this ellipse. Okay. This is this ellipse. This is sigma 1 by sigma yield and sigma 2 by sigma yield, and this is this ellipse. So this is x and this is y. Okay, now sigma 1 by sigma yield is x and sigma 2 by sigma yield is y. So x square plus y square minus xy is equal to 1. This is equation of a rotated ellipse. When you just rotate the ellipse, so this is the equation of a rotated, and this rotation is through 45 degrees. Okay, now so this is the equation of rotated ellipse. Okay, so any point, the application of the theory is very simple. Okay, calculate the distortion energy here. and calculate the distortion energy here. It's very easy to calculate. If you don't know this 4G, so there is no need, because 4G is here and 4G is here. Just calculate this one and just calculate this one. Compare this with this one. If this is greater than this one, failure. If this is less than this one, it is okay. ठीक है ना? It should be, the actual condition should be less than the laboratory test. ठीक है ना? Okay, जी. Thus, just comparison of the maximum shear stress and the distortion energy theory, and the comparison is made here. Is the maximum shear stress theory? One thing is clear from this figure, that there is no large difference between the two theories. You can see this pink color maximum shear stress theory and this blue color maximum distortion energy theory. Okay, this blue color maximum distortion energy theory. Okay, and you can see that there is no big difference between them. Okay, and what is the reason? Maximum shear stress theory is directly related to the maximum shear stress, and the distortion energy is related, the distortion theory is related to the energy associated with the shear stress. ठीक है ना? This theory is related to the energy associated with shear stress, and this is related to the direct shear stress. Since both have the shear stress in their components, so their base is same, so that's why the difference is not too high. Okay, one thing is this one. Okay, the other thing from these two theory, from the comparison of these two theory, is that this six-sided figure is inside this ellipse. You know, they are just touching it at these three locations, six locations. I'm sorry, instead of six locations, but they are touching it. Okay, the rest is the whole. This thing is inside this. So, if anything is safe against the maximum shear stress theory, like a point here, so it will be inside both the ellipse and this six-sided figure. Okay, so if a thing is safe against the maximum shear stress theory, then the body will be safe against the distortion automatically. But it is not necessary that if a body, if a state of stress is safe against the distortion energy theory, it will be safe against the maximum, because this point is safe against the distortion energy theory because it is inside, but this is outside the maximum shear stress theory envelope. So that's why the shear stress theory is more conservative, because it is, if it is safe, then the distortion energy is automatically safe. Okay, so this is next thing. The other thing is that the maximum change, the maximum difference between the two is at this location, where in the second and in the fourth quadrant. Second quadrant, sigma 2 by yield and sigma 1 by yield have opposite sign, and in the fourth quadrant, sigma 1 and sigma 2 have opposite sign. And the maximum change is at this location. Here, this point corresponds to 0.5 of the yield point. Okay, basically this is 0.5. Okay, this point is 0.5. Not this yield point should not appear here. So this is 0.5, and this point, if you just calculate it, so this point is 0.577 yield point. So this is the difference. Okay, so at this point, this is the boundary of the maximum shear stress theory, and this is the maximum, the maximum change in the maximum shear stress theory, and this one, which is 0.577 minus 0.5, so which is 0.077 is the difference between the two theories. Okay, and this is the maximum one. Here the difference is the maximum one. Okay, here the difference between the two theories is the maximum one. Okay, so this is what when we compare the two theories with each other, and these two theories are applicable to ductile material. Now coming to the maximum normal stress theory. Maximum normal stress theory. This is another theory, a third theory. Brittle material such as grey cast iron tend to fail suddenly by fracture with no apparent yielding. In In a tension test, the fracture occurs with the normal stress reaches the ultimate strength of the material. Experiments on brittle material have shown that the ultimate stress at the fracture of a brittle material is only slightly affected by the presence of orthogonal stress. Okay. Now, what this sentence means? That the brittle material, there is no apparent yielding of the brittle material and they fail suddenly by fracture. This is one thing. Okay. Now, when the failure occurs, when its strength reaches its ultimate strength, not the yield strength. There is another, this is another statement, important statement. And in the case of brittle material, let's suppose if you apply a biaxial state of stress, okay, and if you are increasing this, let's suppose you keep this a certain value of sigma 2 and you are increasing this sigma 1, then finally there will be a fracture. And you perform, this is one set. Then you remove this sigma 2 and then perform a test and apply this sigma 1 and increase it and there will be a fracture. When you compare the two results, so there will be a slight difference or there will be no difference between the two. In both the cases, sigma 1, the sigma 1 at the fracture will be same. Okay, it is not affected by the other direction stress, this sigma 2. Okay, which is the base. This is some observation for the brittle material which have made the base for this theory. Okay, so according to this theory, when a brittle material is subjected to a multi-axial state of stress, the material will fail only when principal stresses in the material reaches a value that is equal to the ultimate normal strength of the material in a simple tension test. What he's saying, this is the multi-state of stress and this is the laboratory testing. When this or this become equal to this, so this will failure initiation. Okay, this will give you a failure initiation. Mathematically, sigma 1 should be less than or equal to this one, sigma yield point. You will have to compare it separately, sigma 1 separately, so sigma yield, and sigma 2 separately, so sigma yield. So either this equation will go on or this equation will go on. If sigma 1 is greater than sigma 2, obviously this will be 1. If sigma 2 by magnitude is greater than sigma 1, this sigma 1, then this equation will be 1. So you are getting 4 inequalities with plus minus 4 inequalities. So at the time of initiation, this inequality will become equations, and if you plot these equations, so you will get this one. This is sigma 1 by sigma yield equal to plus 1. Sigma 1 by sigma yield equal to minus 1, sigma 2 by sigma yield equal to plus 1, and sigma 2 by sigma yield equal to minus 1. So you get this square. Okay, this square is the failure envelope. Okay, this is the failure envelope according to the maximum stress theory, maximum normal stress theory. Okay, maximum normal stress theory. So any point inside this will be safe. Any point on or outside this will represent the failure. Okay. Application of the theory is simple. Just compare the maximum normal with the yield. If the maximum normal is less than the yield, okay. If the maximum normal is greater than the yield, then there is failure. Okay. Application is very simple. Okay. Now there is another. So this is the theory which is applicable to the brittle material. Okay. This is not applicable to the ductile material. The maximum strain theory. This theory, which is based on principal strain instead of principal stresses, the previous theory was based on principal stresses, was proposed by French elastician B.D. Saint-Venant, 1797 to 1886. However, experimental evidence does not corroborate with this theory. According to this theory, this is the statement of this theory, that a ductile material begins to yield when the maximum principal strength reaches the strain in which yielding occurs in a simple tension test. This is simple tension test, and this is the biaxial state of stress. So if the strain, the principal strain and this become equal to the principal strain in this, then this will be the initiation. Okay. So what is the principal strain in this one? This is a biaxial state of stress. So epsilon 1 is equal to this one. Epsilon 2 is equal to this one, and epsilon 3, which is the strain in the third direction because of the Poisson effect, is equal to this one. So for simple tension test, the yield strength is equal to this one. And then you will have to compare, according to this theory, you will have to compare this with this one, and this one, or the maximum of this. There will be one value maximum, and if all these three values are less than this one, then this is a safe condition. If they are exceeding this one, then this is the initiation of failure. Okay, this is initiation of the failure, and this is what, when you just compare this with this one, so this, you are getting this kind of an equation. Okay, so this is the maximum strain theory. The maximum strain theory. Okay. Now, comparison of yield and fracture criteria. Now we discuss the three theories, also the strain theory. The strain theory is not dependent upon the, if you are considering epsilon 1, so epsilon 1 has a component of, say, epsilon 2. I'm sorry, sigma 1, so it has a component of sigma 2. So it means that the theory depends on the other direction stress also. Okay, but it is against the maximum stress theory, the maximum normal stress theory, okay, which is dependent upon only the one directional stress. The other direction stress is not considered on. Okay. Okay. So comparison of the yield and fracture criteria. The comparison is made here. You have sigma 1 by sigma ultimate and sigma 2 by sigma ultimate. This one is the maximum shear stress theory. This ellipse is the distortion energy theory. And this square is the, what is the maximum normal stress theory. Okay. Now, tests were performed on different materials in different stress conditions. Okay, in different stress conditions. Malayo kap chai mrawda. Like in this case, this is the case when cast iron, steel cast iron is a brittle material, steel, copper, and aluminum, they are ductile material. Okay, and the tests were performed in different stress environment, in uniaxial environment and in biaxial environment. In biaxial environment with principal stresses of same sign, just like all the points here, these points are what? These points are for when sigma 1 and sigma 2 have the same sign, and these are when sigma 1 and sigma 2 have different signs. Okay, so in all the cases here you can see that the cast iron is these plus signs are for the cast iron, so they are on this line, which is the maximum normal stress. Okay, now if you just look to this point, so this point is considered fail according to the maximum distortion energy theory and the maximum shear stress theory, because these points are outside this one. But according to the normal stress, they are safe. Okay, or they are on the verge of failure. Okay, now any point like there, here, it should be considered safe according to the maximum normal stress theory. And this is the experimental evidence, is that the experimental evidence is showing that it is the other direction stress is not dependent. Okay, the other direction stress is not changing the criteria. Okay, now for all other material, if you just look to all other materials, so they are outside the maximum shear stress theory, and they are they are very close to the Mises theory or the distortion energy theory. Okay, to the distortion energy theory. Now, what it is indicating, that it is indicating that even all these points, they are fail according to the shear stress theory, but they are okay according to the distortion energy theory. So you can say, and all of them, they are on this line. They are very close to this line. So it means that if you are comparing the shear stress theory and the distortion energy theory, so you can say that distortion energy theory is giving you more close resort to the experimental evidences. Okay, so that's the reason that since the experimental evidences are similar, are coinciding, corroborating with the maximum distortion energy theory, so that's why this is the most widely used method, the theory to define a failure criteria for ductile material. Okay, and the normal stress theory is used to define the failure criteria for brittle material. So now we discussed 4 theories, but we are now coming just to 2 theories. Now, non-isotropic material. This is, I think, the last thing, and then we have discussed some 2 problems from the R.C. Hebler book. Non-isotropic material. The 3 theories discussed before are applicable to material having some same strengths in both tension and compression, meaning isotropic material. If you have the properties not directional independent, then it is okay. You can have it like this. You can have same strength. So have same strength if you have same strength both in tension and compression, just like in this case. So this is defined in the failure if you have same strength in tension and compression. But if you have different strength in tension and different strength in compression, then these theories are, the application is, they are not applicable. So some materials such as rock, cast iron, concrete, and soils have drastically different strength in tension and compression. I know about the concrete and about the soil. Soil is having 0 tensile strength and it has some compressive strength. Concrete compressive strength is 10 times greater than its tensile strength, or the tensile strength is 10 times lesser than the compressive strength, and same is the case for rock. Okay, so you cannot apply these theories to these cases. So in 1885, Dugnet modified the maximum shear stress theory to consider the different strengths in tension and compression, just like this one and this one. So this is the tension side. You can see that on the tension side, the strength is smaller, and on the compression side, the strength is higher, both for sigma 1 and sigma 2. Okay, so he converted this. We performed this in tension environment and in compression environment, and he suggested this kind of a failure envelope, Dugnet. Okay, and later on, A. Griffith redefined the Dugnet theory by using the concept of strain energy, and he had made some rounding in this one, because the strain energy, just like the concept of the distortion energy has converted the straight line figure of the 6-sided figure of the shear stress theory to an ellipse. So this is the same. This is converted to this one. Okay. More failure criteria is based on 3 different experiment performed in material, tension, compression, and shear test. Now this concept was later on, in this concept some more modification was made by Otto Moore. Otto Moore, what he did, he performed 3 tests. One test in pure tension. He pulled the specimen and get the strength of the material. Another test in pure compression. Okay, he test the specimen in compression and get the compressive strength. And the other test in pure shear, like a torsion test. Torsion is a pure shear test. Okay, so torsion test, and he get the strength in all the cases. Okay, he get the strength in all the cases, and he had drawn more circle for all the cases. This is for tension. This one is for compression, and this one is for tension compression, meaning a shear. Because you can convert a pure shear case to a tension compression case. Okay, so this is a tension compression. What he did, he just joined the outer point of these using and get the failure envelope of this. Okay, just like the Griffith did. So the Griffith do rounding for this whole case for up to this point, But the more this is a tension, this is compression, and he has just get this one instead of this straight line, he joined it through this envelope. So this envelope curve is same as this envelope curve. Okay, so this is the same envelope curve. Okay, so Otto Mohr did some modification to this and give this modified form of this failure envelope for material for non-isotropic material. So this is the case of non-isotropic material. Okay, now coming to the example we have, we'll try just to finish it up to 10:40. That we'll try to finish it. Then we'll have a break of 5 minutes, and then we'll start. Now this is the some example on the theories. Okay, this is the solid shaft shown in the figure, has a radius of 0.5 inch. So it has a radius of 0.5 inch and is made of steel having yield stress of 36 kSI. So the yield is given to you. This yield is from a simple tension test. Determine if loading caused the shaft to fail. If a design code is specified using the maximum shear stress theory, what would be the result if the maximum distortion energy theory was specified? He's saying that just check this case according to the maximum stress theory and also check it according to the maximum distortion energy theory. Okay. Now, this shaft is subjected to two forces. One is a torque of 3.25 kPa and the other one is an axial compression. So this torque is causing shear stresses at this stress element, and this is causing a direct compressive stress. Okay, so this is causing sigma x is n divided by a, n is 15 divided by a is pi r square. So this is minus 19.10 kSi. This torque is causing, the formula is Tc by j, 3.25 into 0.5 divided by this one. So this is 16.55 kSi. Okay, so the state of stress here is here you have a pure shear and a compressive force. Pure shear and a compressive force. So this is the state of stress. So the first step should be to get the state of stress from the actual body and then to calculate the principal stress. So you will have to convert this state of stress into the principal stresses, and this is the equation. So you got the principal sigma 1 is 9.56 kSi and sigma 2 is minus 28.66 kSi. Okay, so now you got the principal stresses. Now you can calculate the shear. Since according to the maximum shear stress theory, both the sigma 1 and sigma 2 have different sign. Okay, so this will go on. Either you compare this one or you just calculate the maximum shear stress. So how to get the maximum shear stress? You calculate sigma 1 minus sigma 2 by 2, sigma 1 by 2, sigma 2 by 2. Okay, so sigma 1, since in this case sigma 1 minus sigma 2 by 2 should work because they are of different sign. Okay, because this in this minus this, so this will become plus. So that's why. So this is 38.2. Either this divided by 2 and then sigma yield by 2 also, or just remove the 2 and compare this with this one. Okay, so you got that this is case is 38.2 is greater than 36, so it means that this is the failure condition. ये तो fail है, ठीक है ना? But according to the distortion energy theory, this is distortion energy 1 over 4g into this should be less than or equal to 1 over 4g into this. So 4g cancel 4g with 4g. So just compare this with this one. So this is equal to, this is sigma 1 is 9.56, sigma 2 is minus 28.66. Just plug in then this, you will get this one. So this is 36 square. So this is less than, so distortion energy is okay. Because this side is less than this one. This side is less than. So the case is if the code is using the maximum shear stress theory, okay, then this is the failure condition. But if the code is using the distortion energy theory, then this is a safe condition. Okay. Now this is the last problem. The solid cast iron and shaft shown in the figure is subjected to a torque equal to 400 pound-foot.
determine its smallest radius so that it does not fail according to the maximum normal stress theory. Okay, this is a cast iron, and cast iron is a brittle material, so that's why he is using the normal stress theory. A specimen of cast iron tested in a tension has an ultimate stress of 20 kSI. Okay, so this is a solid shaft. It is subjected to a torque of this one. Its radius is R, and R is unknown, but he has mentioned the ultimate strength, and you'll have to calculate these stresses. So the maximum, the only force applied to this shaft is the torque. So the state of stress will be a pure state of stress. Okay, so tau maximum is equal to Tc divided by J, so it is in terms of R, but the state of stress is like a pure shear state of stress. It's a pure shear state of stress. When you just convert this pure shear state of stress to the principal, then you will get this one. If this is tau, then this one, sigma 1 will be equal to tau, and sigma 2 will be equal to minus tau. Okay, so here you can see that for this case, tau maximum is this one. Okay, so sigma 1 is minus sigma 2 because sigma 2 is negative. So sigma 1 is minus, both of them are equal to tau is equal to tau is equal to this one. Now, according to the normal stress theory, sigma 1 should be equal to sigma ultimate. So just make this equal to sigma ultimate, which is 20,000 pound per square inches, and get the value of R. So the radius should be 0.535 inches. If the radius is less than this one, so according to the normal stress theory, it will be a failure condition. So this is the case. Now we can have a break of about 5 minutes, and then after 5 minutes, Azaz will assign the quiz to you, and you will have to submit it before 11 o'clock. ठीक हो गया ना? 11 बजे जो है वो आपने इसको खत्म करना है. Azaz?
11 o'clock.
Yes, sir.
11 o'clock, you will have to submit it by 11 o'clock. So you will be having 35 minutes. Exactly, चिकमने बताया assign का, ठीक था? Assign it at 10:25 पाने, ठीक था?
Sir, stas tarafse time ne us kadai ki sir.
मां सर 10:18 भी. ना खुदा बगड़ाई बाने, खुस्ता बाने, पकार जिस्ता गड़ाई बाने उसी का ना सर से टाइम. साल कंप्यूटर गड़ाई किस?
जमा सर 22 थे बस सर जो 3 मिनट और assign करो.
ना 22 बोले 22 सारा गड़ाई सलूर मिनट का माह के दा.